This video is going to link kinematic equations and calculus to make our lives much easier. So a few reminders before we get started. In physics, we represent position using x. We say, okay, I can write equations for my position where I define position as x. I can write v represents velocity. We say velocity is defined as the change in position over the change in time. We could calculate this by saying I'm going to take my position at some later time 2 minus my position at some earlier time 1 over my change in time. So time 2, my final time, minus time 1, my initial time, and then our corresponding change in position. And we could represent this with a delta x over a delta t, where a delta, this little triangle, represents change in x over our change in time. It's just a shorthand way of writing this. And we also said we could define instantaneous velocity as the velocity when we take this little expression, the change in x over the change in time, and we shrink that time interval until it gets really, really, really small, instantaneous. Right at that time moment, what is our change in x? We represented this as the limit of this function as that little delta time goes to 0. So we shrink that time interval. How does our change in x relate? What does it do? That's our instantaneous velocity, instantaneous change in x over that instantaneous change in time. And very much related, we had acceleration, which we wrote as a. Acceleration is defined as the change in velocity. So notice it's very similar to velocity, which was the change in position, but now acceleration tells us how our velocity is changing and how it's changing with respect to time. So once again, very much like this, we say, well, instead of change in position, we are doing change in velocity at those two time places. And we could represent this with a delta v over a delta t, our change in our velocity over our change in time. And we had instantaneous acceleration, which, just like instantaneous velocity, is the limit as we take that little time interval and we take it as small as we can go, instantaneous, that's delta v, over delta t. So how does our change in velocity respond as we shrink that change in time to infinitesimal? Instantaneous change in acceleration. Okay, now just to remind you, position is units of meters typically, so a distance, meters, some length. Velocity is, since it's change in position over change in time, it usually has units meters per second, but sometimes, use kilometers per hour or some other length over time. And acceleration, because it's change in velocity, well, velocity has units meters per second, and then we divide it by seconds again, so we'd say meters per second, which is often written as meters per second squared. So we are describing our changes ever increasing relative to time. Okay, now, as we're linking this to calculus, there are a few ideas that I'm going to operate off the assumption that you know. If you do not feel comfortable with these, you got to come see me. So in calculus, you learned how to take a function like y equals 5 plus 4x plus 3x squared. And you learned how to do the derivative of this with respect to x. So you learned in calculus, we write that dy dx, our change in y relative to our change in x. And we said, okay, if I have a constant 5, how is that changing when I change my x? Well, when I change my x, 5 is not changing. 5 is a constant. So the change in 5 when we change x is 0. It's not changing. But then we go over here and we say, well, 4x. How does that change when I change my x? And this does change. I change x by a little bit, and this changes by an amount 4 times. So we were able to take the derivative of 4x with respect to x and get 4. And then you learned in calculus. Now we get a little bit more interesting. We're taking x squared. What happens when I have an x squared term? Well, it turns out when you change your x, this responds in a way that's quite nice to take the derivative. We bring our exponent down, multiply it out here, and then we drop this exponent by 1. So 3x squared ends up becoming 2 times 3, which is 6, times, and then instead of x squared, we do x and we drop this exponent by 1, which turns out to be 1, which is just x. So when you took the derivative of a function like this, you get a constant with respect to x is changing not at all, so 0. This 4x changes as 4, and this 3x squared changes as 6x. Once again, this I'm sort of operating that we are comfortable with. If you are not, you've got to come see me. Okay, now if we took this sort of idea and we put it in terms of just general variables for our constants, we could write something like a plus bx plus cx squared. And if we do our derivative of y with respect to x, we'd get 0 plus b plus 2cx, where we brought that 2 down, and then this exponent dropped by 1. Okay, very much the same, just with some variables. All right, let's add some physics in here. So in physics, when we were talking about our kinematic equations for constant acceleration, we said we could represent position x. Remember, we said position was defined as x. That's how we represented it. Our position x was equal to wherever we started out at, our initial position. You know, if you start at 10 meters or 100 meters or negative 20 meters, whatever your initial position is, plus our initial velocity times time. So how fast are you going right at the beginning? That v naught represents at time 0 times the amount of time that we're traveling for. Now, if we didn't have any acceleration, if it was just a constant velocity, this would be our equation for position with constant velocity. So x equals where we start at plus how fast we are going, because it's constant, times time, right? How far do you go if you start at 10 miles and you travel 60 miles per hour times 2 hours? Well, you'd multiply that 60 miles per hour times 2 hours, get 120 miles, plus your initial position gives you your final. So that's for constant velocity. But we said, well, we're not doing constant velocity. Our velocity is changing. We have a constant acceleration now. So we consider our initial velocity. How does our initial velocity affect us? But since our velocity is changing, we said we added this little 1/2 at squared term. Now remember, this is for constant acceleration. And then that gave us sort of the amount of change in our position due to the acceleration. Okay, now if we come in here and we highlight just our constants, those are our constants, right? That's a constant initial position, a constant initial velocity, and then 1/2, of course, is a constant, and our acceleration is a constant. So we are going to mark all of those in blue. Now notice, time is the thing that is changing in this case. Okay, here's our calculus. If you want to see how does this change, how does our position change with respect to time, we would do just like you did up here. How does y change with respect to x? Well, now we're saying how does my position, how does my x change with respect to time? So we're doing the derivative of x with respect to time. All right, just like up here, constant changing with respect to x. Well, it didn't change. So this constant changing with respect to time, well, it's not. It's constant. So that becomes a 0. This one, our initial velocity times time, well, a little bit of change in time is going to cause a change of v naught in our position, right? Just like up here, 4x, derivative with respect to x gave us 4. V naught with derivative with respect to t is just v naught. There's our two constants, there's our two constants. Okay, and just like up here when we had an x squared term and we pulled that exponent down and minused it by 1, we're going to do the same thing here. We have a t squared, and we're doing the derivative with respect to time. So we bring our 2 down. Well, 2 times 1/2 is just 1, so we get an a. There is no sort of 1/2 here. That 2 canceled. And t, when we drop its exponent by 1, we just get t, just like up here, just like up here. Okay, so we're almost in the sort of form that you're familiar with, but we need to make one little quick note. So remember, we said instantaneous velocity, can't even see my letters there, instantaneous velocity was defined as the limit of this delta x, delta t, as our delta t went to 0, so tiniest change in time, instantaneous change in time. How did our position change? Well, this in calculus is written as dx dt. It means when that time interval is just infinitesimally small. Well, wait a second. The change in velocity, the change in position with the change in time, that's our instantaneous velocity, that's just v. So dx dt is velocity. It's velocity at a given time. So right here, this equation, dx dt, we can rewrite dx dt as velocity. That's what it is. And then we come over here and we say, well, okay, that's 0. It's equal to its initial velocity plus its acceleration times time. And this should look super familiar to you. This is a kinematic equation. Kinematics equation. So going from our position, which itself was a kinematics equation, taking the derivative of the position with respect to time, popped out as another kinematics equation. Our velocity at any given time is equal to our initial velocity plus the change in velocity times time. Remember, acceleration here was the change in our velocity with respect to the change in time. So if you change your velocity, 9.8 meters per second every second, well, you multiply it by the number of seconds you've been traveling, and that tells you the change in your velocity. So your velocity just equals your initial plus that change times time. Boom, kinematics equation coming off our position equation just with a little bit of calculus. Okay, now we're not quite done. So once again, we can do the derivative of this equation with respect to time. We can say, well, okay, if I care about how my velocity is changing with respect to time, I'm going to do my derivative of the velocity with respect to time, dv over dt. Now, velocity initial changing with respect to time, it's not. It has no time term multiplied by it. It is a constant, right? We'll come back in here and we'll highlight our constants. There's a constant, there's a constant. So the derivative of this with respect to time is just 0. And over here, the derivative of at with respect to time is just a. Right like here, derivative of v naught t with respect to time was v naught. Derivative of at with respect to time is just a. And just like we said, our instantaneous velocity was defined as the limit of delta x over delta t. As delta t went to 0, we can say the instantaneous acceleration is the limit of our delta v over delta t as that time interval went to 0, which, just like up here, we can say dv dt is our acceleration. So this guy right here is acceleration. The change in velocity with respect to time is acceleration. And it equals a. Well, that's kind of a silly equation. A equals a. Well, that was the one that we wrote as a equals a constant. Because remember, this is for constant acceleration. And once again, we are staring right at one of our sort of kinematics equations, although we represented this on our graph as a constant acceleration. Okay, so check it out. Going from position, taking the derivative, gave us the velocity. Derivative of position equation gives you velocity. Okay, so the derivative of a function gives you its slope. Remember we said the velocity, the change in position over the change in time, that was the slope of this graph. So we spent all that time trying to pull slopes off of our position time graph to get the velocity. Well, that's why doing the derivative of this with respect to time, the derivative of our position equation, gave us our velocity equation, gave us how our graph of velocity works. Beautiful. Position to velocity using just a little bit of calculus. And we did it again. We said, well, the derivative of the velocity, the velocity equation gave us acceleration. And in this case, our acceleration is constant because typically in our world, most motion can be represented with constant acceleration. So there you have it. A little bit of calculus makes physics so beautiful.